Welcome to day 5 of our challenge. Today we're going to focus on how to fix violations of assumptions for each of the different regressions. For the case study today, we're going to focus on linear regression. But the goal is, how do we detect that violations have occurred in terms of the requirements, and then how do we fix them? Now, before we proceed to the hand part of our demo, there's a very important conception we need to clarify. Because when we start working on fixing some of those violations, one of the things we will be doing is adding quadratic terms to our model. And for some people, let's say, well, this is supposed to be linear regression. Why are you adding a quadratic term? A quadratic term is not linear. The mistake here is assuming that when linear regression says there's a requirement for linearity, assuming that we're referring to the individual predictors. The input age or sex are like so what is needed to be linear is not individual variables or the inputs, but the coefficients. The coefficients, the predictors themselves can be of a shape or size, right? We don't care. So it is okay to add quadratic terms, and we'll be in a minute. But another question that often comes up is, what exactly do we mean by linearity? What does it mean for the model? Well, think of it like a budget. If you have a budget, you have different line items, and for each line item, you have the rate times the number of items. So, for example, the project manager works at $200 per hour, and he worked for 120 hours. So the total due to them is 24,000, which is this times this. That is how we get the subtotal for each line item, and the grand total is simply a sum of all the subtotals. So you can see here that this budget is linearly constructed because the only mathematical operators that are going on here are multiplication and addition. That is the only thing going on. So when you look at a linear equation, you can see also the exact same thing happening. Two things only involved, times and plus, and that's what we mean by linearity. Now let's go to the Calculus platform and see how we can actually set up a regression model and test the alignments. We're going to use the project we've been using for the past few days, the research question exploring whether there's an association between quitting smoking and change in weight. So let's fit our regression model by coming down here and selecting a linear regression model. We'll select our variables. Our primary exposure is quitting smoking, and we have several confounders of the relationship. Oops, sorry, I selected the wrong variable here. Our outcome variable is weight change between 1982 and 1971 baseline. That's our primary outcome. Our predictor variables are whether you quit smoking. That's our main primary exposure. And then we have several confounders that we want to control: your levels of exercise, and your race, and your sex, your whether you how much education you have, how much activity you have, your marital status. That's variables that are continuous, like age. Let's select that. Where's my mouse cursor? Okay, age. We have the weight at baseline. We have your measures of smoke intensity and duration. So smoke intensity and smoke years. All right. So those are the variables in our model, and then we have the reference category selected automatically. For the sake of time, I won't make any changes, but again, you can change any of this to fit what you want. For example, I can change this to have the worst category as a reference group. The same thing with exercise levels. I can choose individuals who have little or none as a reference. And now we're going to fit this model and then come back and check the diagnostics for the model to see whether or not the assumptions for linear regression are true in this model. So let's wait for a few seconds for the model to defeat, and then we can then look at the diagnostics. Okay, great. So we have the model here. This is our primary exposure. with a coefficient of 3.42, we interpret this to mean that to those who did not quit smoking, those who quit had a 3.42 higher mean body weight, suggesting that quitting smoking is associated with higher body weight compared to not quitting, and that was statistically significant. For now, we're not really interested in the results for today's demonstration. We're interested in the fit of this model. How well was it fit? So we're going to come to the metadata, which has things like the total sample size and the complete cases that were analyzed. But what we're really interested is in the table down here that talks about indicators of model performance. First things first, we have the AIC, which we'll be using quite a lot. It compares model fit versus model complexity, and smaller values are better. So when we fit the next model, we're going to come back and compare the two models with their AICs. Now, the platform also evaluates each of the four assumptions for linear regression for you. There is linearity, homoscedasticity, independence, and normality. And in the far left right column, explains in simple language whether those assumptions met or not. So based on the test statistics here, you can see that non-linearity detected, which simply means that the assumption for linearity has not been met. Same thing here, we see that the assumption for homoscedasticity has also not been met. There is no auto-correlation power, which means that the assumption for independence has been met. And lastly, residuals not normal, meaning that the assumption for normality has not been met. So now that we know the problems, how do we fix them? Well, the issue of non-linearity, we can try to address it by adding quadratic terms. We will add quadratic terms for the different continuous variables in our model, and we'll see how that improves fit. For this, we can add robust standard errors and see how that improves the model fit. We don't have a problem with this. For residuals not normal, what we could do is we could look at alternative models. We could, for example, consider transforming our model to another form. We could use median regression. But for now, let's on the side burner, and let's look at these two assumptions, and let's see how we can address them. We'll come to the issue of not normal residuals at some more time. So let's refit this model by coming to rerun, and this time we would make some changes to the model. We'll come to model optimization, and first we are going to come to add quadratic or cubic terms to your model. It is important to add a quadratic term in this case, seeing that assumption of met. When we put a linear term in a model, we are assuming that the relationship between the outcome and the predictor is linear, that one increases linearly as the other increases. That may not be true. It could be that at some point in, for example, one's age, the weight gain is more active than at other points in your age. So the relationship might be curvilinear. Surely there are some parts of it that are linear, but other parts might be more curved. So that reflects a quadratic relationship. So in that case, we want to add quadratic terms to our model. So we're going to do that for all the continuous variables in our model. Here you see the platform indicates the variables that are already in your model with this icon here. So we're going to select these variables and choose quadratic terms, add them. So what the platform does is that it centers each of these variables. Centering simply means that the platform takes the mean of each variable and subtracts it from each observation. The reason we do that is to prevent collinearity between the linear term and the quadratic term. So you can see here that the platform has taken, for example, the weight in 71. It has removed the original variable and added a centered version of that variable, and also created a square from that centered version. So you have WT71 underscore C, which is the centered form of that variable, and then C squared, which is the square of this. So centering is done primarily to prevent issues of collinearity in a model. So we apply all suggestions, and now the other thing we want to do is to ensure that we allow robust standard errors. This is very important since our data shows that the assumption of homoscedasticity has not been met. So we can change the number of decimal places to something like 3 if we wanted, depending on the use case, obviously. And let's apply those preferences. So now we can estimate. So now the model is being fitted with two important changes. One, we've added quadratic terms to the model, and that is to address the issue of non-linearity. We've also added robust standard errors. So here we see the results. Again, we're not very interested in this. What we're interested in is model performance. So we can come back to metadata, and we can use the AIC. We can compare the AIC in this model. Just looking at this, you can see that the AIC has become much smaller, which means that it is a better model than the other ones. Now, apart from this case we've made, there are also a lot of other procedures you can do, for example, to address issues of non-normal residuals. You can choose to, for example, your outcome variable. You, however, want to be very careful with transforming and paying very close attention to issues of interpretation, because it's not just about fitting the model, it's also about making sure people understand what it means. If we're going to use something like a log transformation, we want to make sure that the variable does not contain zeros or negative values. As a matter of fact, the platform will not even allow you to proceed if your variable does contain those offending values. So, but overall, those are some of the tools we can use to check for the performance of our model and to fix some of the issues that may arise from violations. I look forward to reviewing your tweets. If you have any questions, please drop them on LinkedIn and tag us, and we will respond accordingly. Thank you very much.